Finally, always be aware of if a tornado is starting to occlude and dissipate. This is especially important if you're anywhere north of the circulation. Occlusion occurs when the rear flank downdraft wraps completely around the tornado, cutting it off from the warm, moist inflow that feeds it. As this happens, the tornado can make a sharp turn to the left or north. This can put anybody to the north of the circulation in a very compromised position should this happen. The good news is that you can actually forecast deviant tornado motion ahead of time using a hodograph. This can and should be done ahead of time when you're forecasting for a storm chase using forecast soundings, or you can use observed soundings in proximity to your target area out in the field. This is a simple technique that was devised by Nixon and Alan 2021, and we start off by finding the mean wind in the lowest 500 meters of the atmosphere. Now, there's not a 500 meter point that's explicitly labeled on the hodograph, but a nice little tip to know is that this purple line right here, that is the 0 to 500 meter wind shear vector. So the endpoint of this line is your 500 meter point. And this is going to be displayed on all soundings that you'll see from the Storm Prediction Center, whether it's observed soundings, or for modeled soundings on your favorite model sites like College of DuPage and Pivotal Weather, as long as the effective inflow layer base is at the surface. Basically, if this bottom blue line here extends from the surface point on the hodograph. If it's not plotted, you'll just have to estimate the location of the 500 meter point on the hodograph. So we want to find the mean or average wind in that lowest 500 meters of the hodograph. Just eyeballing it, it looks like it'll be somewhere kind of right in here. Doesn't have to be perfect, and it's not going to be right on the line because we have a little bit of curvature there in the low levels of that hodograph. But for our purposes here, eyeballing it is going to be okay. So there's our first point. Then we find the storm motion vector, that bunker's right storm motion, which is right there. We then find the midpoint between these 2 points, which looks to be about right in there. We then draw a vector from our origin to that point, and that is our deviant tornado motion vector. We compare that to our storm motion vector. I'll draw it in blue here. And the larger the difference is between the deviant tornado motion vector and our storm motion vector, the more deviant tornadoes are likely to be. And this is pretty significant deviance here. You see quite a decent angle between those two vectors. So that shows that tornadoes will tend to be quite deviant when they're occluding, and they'll tend to deviate pretty hard to the left of the storm motion.
Getting home alive is the goal. That's why these rules matter. Free ebook link in description.
How about another example? So here is our 500 meter point right there. Let's find the mean wind in the lowest 500 meters. Kind of in the center of this triangle it would be, so kind of right in there. We then find the storm motion, which is there, and then find the midpoint between the two. Looks to be right in there. I'll draw in our deviant tornado motion vector. Looks like that. And then compare it to our storm motion vector. And you see a much lesser angle between these two vectors than in our last example, which means that tornadoes may not tend to be as deviant in this environment. Slow-moving storms tend to produce much more deviant tornadoes than fast-moving storms. Regardless, you should always use extreme caution when north of a tornadic circulation. Always have your escape routes handy, have your head on a swivel, and maintain situational awareness at all times. Finally, I wanted to briefly discuss when you should pounce on a storm quickly versus when you should give it some time to organize. The situations in which you should get onto a storm immediately are, number one, when the storm is anchored to an outflow boundary. Outflow boundaries can be breeding grounds for tornadic supercells. Along the outflow boundary, there is enhanced low-level shear and vorticity, or spin. Updrafts that go up along the boundary can tilt and stretch that vorticity into the vertical to create landspout tornadoes, even before the storm becomes mature. And storms that anchor to the boundary, which means that they track along or latch onto the boundary, they operate in that higher low-level shear environment, which means that those storms can have a much higher chance of producing tornadoes than storms that are not anchored to the boundary. Also, when you have an overlap of strong low-level instability, which is measured by 0 to 3 kilometer CAPE or 3 CAPE, and surface vorticity or spin, that's another situation in which you want to pounce on the storm quickly. Strong low-level instability can tilt and stretch that spin or vorticity at the surface into the vertical underneath updrafts, which can aid in tornadogenesis in supercells. This process can happen fairly quickly, so when you see those two ingredients overlapping, and storms going up in that overlap, you want to get on the storm immediately. In most other scenarios, storms need time to organize, particularly if you have strong deep layer wind shear, or if you have strong storm relative inflow like we talked about. You need a lot of those auxiliary cells on the rear flank of the storm for tornadogenesis to occur, and that may take quite a while. So in most cases, you don't have to rush to get on a storm if you see it going up, but when you want to pounce quickly onto a storm is when that storm is anchored to a boundary and or there's strong low-level instability and vorticity overlapping where that storm is occurring.
Remember to check out those links in the description below, and then watch another video.